Hello and welcome back. So this is actually going to be our last bit of new material for this unit. So what you're going to find is that most of our units are quite a bit shorter than that first unit. That first one was, to throw a little statistics term at you, a bit of an outlier. Hey yo. All right. So what are we doing today? We are assessing normality. Now, why is that something we need to do? So last time we looked at the normal distribution and we started using things like NCDF and inverse norm. And I said that these curves basically served as an approximation for the actual histogram. Now, it turns out that they're a very accurate approximation, but an approximation nonetheless. Now, for them to be an accurate approximation, the underlying distribution or the underlying histogram has to be relatively normal in shape, right? If the underlying distribution is not relatively normal in shape, then all of those estimations, approximations that you get from NCDF are basically useless. All right, so normality is basically a precondition or a prerequisite for using NCDF and inverse norm. If the underlying distribution isn't normal enough, and we'll kind of talk about that a little bit as we go through the notes, then all that other stuff is irrelevant. All right, so how can we go about assessing normality? All right, so the first thing we can do is we can create a histogram. And we can look at the shape of the histogram. Is it relatively symmetric? Does it have the bell shape that we're used to seeing, where you have a peak right in the middle and then it tails off in both directions to the left and to the right? And hopefully there should be no major outliers. All right, so these are things that we would be looking for when we create a histogram. As far as the center is concerned, we're going to hope that the mean is relatively close to the median. All right, when you're dealing with real world data, they're unlikely to be exactly the same, but we're going to hope that they're relatively close. All right, so that's step one, is we can say, create a histogram, look at the shape, check the center, see what's going on there. All right, step two is to check the 68, 95, 99.7 rule, right? Which is just to make sure that the data is approximately distributed in a normal fashion. So we would determine 1, 2, 3 standard deviations above and below the mean. So basically find the cutoffs. Count the values within 1 standard deviation of the mean and find the percent. Compare this to 68%. Repeat for 2 standard deviations, repeat for 3 standard deviations, and make sure that they come pretty close to this rule here. Again, it's unlikely to be exact, but we're hoping that it's relatively close to 68%. We're hoping that it's relatively close to 95%. And we're hoping that it's relatively close to 99.7%. All right, so we're seeing, does it follow the general pattern that we would expect? All right, and then the final one is something called the normal probability plot. And this is our most sophisticated and probably our most valuable tool. A lot of times we start with either of these because they're just kind of a quick and easy way to say, is this good? Is this not good? The normal probability plot is the more robust test of whether something is normal. Now, previously, like we kind of would go through this progression because this is actually very labor intensive to make. Thankfully, now we have technology that can do it for us, but let me write the definition and you'll see why. So the normal probability plot is a scatter plot showing the variable as the x-coordinate variable, you could also think of that as observations. All right, so that's the observation values, whatever your data is about. And the z-score of each observation's percentile as the y coordinate. All right, so what does that actually mean? All right, what is the z-score of each observation's percentile as the y coordinate? All right, so let's just pretend we had a very simple distribution that only had, we'll say 4 things in it. So we'll just say the values were 5, 11, 12, and 15. Right? So those are my values. So for every single value, I would have to calculate the percentile. All right, so let me say, all right, this 11 here has a percentile of, there's 1 observation below it out of 4 observations. So this would be at the 25th percentile. I would then do an inverse norm of 0.2501. That would give me a z-score. And I would have to do that for every single observation in my data set. All right, so I would calculate its percentile. I would use inverse norm. I would get that as a z-score. And this right here is the y coordinate on my plot. All right, so you can see it's a very labor-intensive process without the aid of technology. Now, what does this actually show you? Well, a straight line, so if your scatter plot ends up in a relatively straight line, that represents a normal distribution. If the leftmost dots are to the left of the line, drawn through the main body of points, the distribution is skewed left. If the rightmost dots are to the right of a line drawn through the main body of the points, the distribution is skewed right. And we're going to look at some examples of this in a little bit, but the general idea is if you end up with things that are like relatively in a straight line, that's good. If you end up with something like this, where when you draw a line, whoops, this would be the left skew, this would be the right skewed one. But if you draw a line through the majority of those points, this would be right skewed, this would be normal, and then this one right here. What would be the way to draw this? All right, so it might look something like this, where you've got the main line going right through there, and then you've got points off to the left. Right, so that would be left skewed there. All right, again, we're going to take a closer look at this later in the notes, but this is sort of the general idea. If they're relatively in a straight line, that's going to represent a normal distribution. If they're off to the right of the main line, it's going to be right skewed. If they're off to the left of the main line, they're going to be left skewed. And we'll talk a little bit more about why this would happen later on in the notes. Okay. So let's run through an example. All right, so here we have unemployment in the US. We have unemployment rates in 50 states, and we want to assess is this data normal? All right. Can we use the normal distribution to approximate what's happening in this type of situation? All right. So the first thing to do would be to sketch a histogram. So I've already gone and entered all of those values into L1. All right. I can go to my stat plot. I can make sure that stat plot 1 is on. I can choose the histogram. And then if I go to zoom 9, I can get a quick sketch of what the histogram looks like. All right, so I'm not really worried about like the individual counts here. I'm just trying to get like an overall sketch of the general shape. So we've got one bar that goes here. We've got one bar that's a little higher than that. We've got two bars that are a little lower than that one to the left. And we've got one down here. And then we've got one over here. Okay. So what's the shape? Well, there's a few things we can say. It's somewhat symmetric with the exception of like this one over here. All right. So is it perfectly symmetric? No. But real world data isn't going to be perfectly symmetric. So we can say relatively symmetric with one potential outlier. And the other thing we're going to say, because this is important for a normal distribution, is that it's unimodal. All right, normal distributions just have that one kind of bell-shaped peak. So it is good that we're not seeing like multiple peaks throughout our distribution. Now, as far as the center goes, the data is already in my calculator. So I can go to stat calc, one variable stats. I don't have a frequency list this time, so let me clear that out. And if I run that, I can see that the mean is 8.682. 8.682. And the median is 8.5. All right, so the mean is a little higher, which is not necessarily surprising because we have this observation out there, but they're relatively close. All right, so the mean and median are relatively close. So from this, we have some concerns. All right, we have some concerns because we have this out here, but there's no like massive red flag that says, uh-oh, this definitely is not going to work. So since there are no red flags, we're going to proceed with our analysis. Like if we saw something that was blatantly skewed and these two measurements were way apart from one another, we could stop. There'd be no reason to go any further. But since we're kind of in this like gray area here of like, I don't know, like parts of it seem okay, parts of it are a little worrisome, we push on. All right, so now we can check the 68, 95, 99.7 rule. So the mean we already got was 8.682. All right, now the standard deviation, we can use the population because we have data from all 50 states. So we can say our standard deviation is 2.202. We'll just use the same number of decimals. 2.202. So then it would be a matter of just finding those various ranges, right? What are the ranges if we go one standard deviation above the mean and one standard deviation below the mean? All right, so we're basically going to take this 8.682 and we're both going to add and subtract 2.202. right? And that's going to give us our two cutoffs. All right, so we would then go say, all right, how many observations are between 6.48 and 10.884? And then we would just go through and we would count those. So we'd say, all right, 6.48. So we'd start with these right here and say, all right, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I screwed something up. Oh, no, I didn't. I just stopped at the average instead of my range. All right, so let me do that again. So I'm starting right here. So I've got 3 there. I've got another 10 there is 13. I've got another 10 there is 23. 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. All right, so I've got 35 observations that are between these two benchmarks. 35 out of 50 is 70%. Right, so far, so good. All right, again, it's not going to be exactly 68%. I mean, it could be, but we're still in the ballpark. All right, so now we would just do this again, and now it would be 8.682 plus or minus 2 standard deviations. So that would be 4.404. That's 2 standard deviations, which gives us a range from 4.278 up to 13.086. So that basically means everything from this top row except the 4.1. So there's 9, 19, 29, 39, and then 40, 41, 42, 43, 44, 45, 46, 47, 48. All right, so there's 48 observations that fall between these two values. 48 out of 50 would be 96%. So again, not exactly 95%, but we're on the right track here. So 8.682 plus or minus this time 6.606, which is just 3 standard deviations. And that would give us a range from 2.076 up to 15.288. All right, and with that range, we are capturing all 50 observations, which works out to be 100%. So the conclusion is the data pretty closely follows the 68, 95, 99.7 rule. It's not exact, but you don't really expect things to be totally exact when you're doing this sort of stuff. You're just seeing, is it in the ballpark? All right. So that brings us to our final tool here, which is the normal probability plot. Now, again, doing this by hand would be incredibly tedious. For every single one of these observations, you're figuring out its percentile, and then you are converting that percentile into a z-score, and then you are plotting it on a graph. We are not going to do that by hand because that would take probably 2 classes. All right. So instead, we're going to go to stat plot. We're going to make sure stat plot 1 is on. And then it is the very last choice there, right? That is your normal probability plot. The data list should be L1. The data axis, we're always going to keep it X. You can flip it around, but we're going to keep it as X. All right. And then again, you would just do zoom 9 for zoom stat. And that is your normal probability plot. All right. So let's get that sketched over here. So we've got this right here. And then it's something like this. Okay. So if we look at this, basically all of our points are falling on a straight line. All right, there's no real curve to our points. And if there's no real curve to our points, that's suggesting that we're in good shape. So we can say that the plot is basically linear. So we can assume normality. All right. Be that normality. All right. So this is sort of the three-step process of determining whether data is normal. Right? You can start with a histogram just to make sure there's no like immediate red flags. Then you can move to the 68, 95, 99.7 rule just to make sure it's following that general distribution. And then you can finish it off with the normal probability plot to make sure everything falls the way that it needs to fall. All right, so let's take a closer look at some of these normal probability plots. All right, so what we have here is a faded histogram that's pretty hard to see. So let me pause this for a second and redraw over it. All right, so now I have a graph that's very easy to see. And it's pretty obvious that this is a right skewed graph. All right, we've got this tail going off to the right here. Up above that is the normal probability plot for this histogram. So you can see here, if I draw a line through the main sort of bulk of the points, all right, I'm getting these values to the right of the line, which is supporting the notion that it's right skewed. Now, sometimes kids are like, well, how do you know whether you should draw the line this way or whether you should draw the line through the points like this? And what I say is it doesn't actually matter because either way, you're getting those outliers or the ones that break the pattern are showing up to the right of the line. So whether you draw your line through this and say, oh, these are off to the right, or whether you draw your line this way, they're still going to end up off to the right. So you're going to reach the same conclusion. Now, again, let's kind of think about why this makes sense. All right. So first of all, since the normal probability shot shows an obvious curve pattern, the distribution cannot be approximated with a normal model. This is basically saying if you tried to use a normal model on this type of distribution, it would still give you answers, but those answers would be irrelevant. All right. They wouldn't really reflect what's going on. And then it says, actually, since the point on the far right are larger than expected in terms of the x-axis, we know the distribution is skewed right. So again, let's just remember how this is generated. So if I've got this observation way over here, it would give me a percentile of like, 90 some percent. All right, it's going to be really high because it's most of the observations are below it. I turn that percentage into a z-score, and it's going to give me a z-score of whatever, 2 or 3 or something like that because it's high there. So what's happening here is these values on the x-axis are way bigger than we would expect given what we have down here. Based on these data points where we have this bulk of the information, we would expect a z-score of 2 or 3 to only have an x value of like 200. But instead, the percentile that gives us a z-score of 3 is being attached to like a value of like 600. All right, these values are way too high compared to what we would expect or compared to a normal distribution. Right? It's basically saying like you shouldn't have X values this big if your data is normally distributed. Right? Those X values that are 1 or 2, 3 standard deviations from the mean should only be about out here, but instead you're getting values way out here, which is breaking sort of the overall pattern of what would be expected, which is why we can say, oh, this distribution is actually sort of right skewed. And then the same thing can happen in reverse for left skewed, where you're getting things that are much lower than would be expected based on a normal distribution. All right, so that's kind of the general idea, is that you're getting values that are just out of whack with the normal distribution, and the normal probability plot gives you a way to sort of assess that by turning everything into these z-scores based off the observations percentile. All right, so again, you're never going to have to make one of these by hand. I will ask you to like create one on a calculator, and then you do have to be able to interpret it, right? And interpreting it really goes back to what was on the front page here, which is a straight line represents a normal distribution. If the leftmost dots to the line, if the leftmost dots are to the left of the line, which is this one down here, it's left skewed. If the rightmost dots are to the right of the line, the distribution is right skewed. All right, so just making sure that if you see one of these plots, you know how to read it, interpret it, and you can say, oh, that distribution is either normal, that distribution is right skewed, or that distribution is left skewed. All right, so that's basically what I'm going to be looking for when it comes to these normal probability plots. All right, so that is it for today. I hope this was useful. And if you have any questions, make sure you reach out. All right, bye.